Good afternoon, everyone, and welcome to webinar 3 in the series of Climate Action and Sustainability, our lunchtime lecture webinar series. I suppose hosted by myself, John Gallagher, in the Department of Civil Structural Environmental Engineering in Trinity College. And as for those of you who have joined our previous 2 sessions, we've had an excellent turnout, and I see the numbers are starting to rise as people are joining us today as well. For another excellent talk from our speaker, another colleague here in engineering. But as the series details are being released, as you'll, for those of you who are following us, we're expanding this beyond engineering to across the university. So please stay tuned to the broad range of speakers that are coming. So just to note, I suppose, why are we doing this? You may have already joined us, but it's all about us trying to share knowledge and perspectives on how we as academics in Trinity College are addressing national and global challenges, and how our work feeds into supporting that. We have 12 webinars in total. We're in part 1 at the minute, with this being the third of 4 of part 1, but part 2 starts immediately after. My apologies for those of last week. We had to reschedule our speaker to next week, and I hope you can join us again for that. And as I said, details for part 2 are already available, and part 3 will be released very, very soon. So with all our speakers, these 2 slides will maybe be an intro for their context around national priorities for the Climate Action Plan, and as well as that, more international focus as well to address in terms of the UN's Sustainable Development Goals. So briefly, our speaker today will just highlight maybe where their work fits into this national and global context. And I am very happy and welcome our speaker for today, colleague Professor Aonghus McNabola. Been working with Aonghus for quite a few years at this point, to say the least, Aonghus. And his focus, I suppose, is a very unique one in terms of it's not just about focusing on small hydropower. It's about the journey that he's taken in relation to from a concept to a commercial enterprise. And it shows, I suppose, it demonstrates that our work in the university isn't just internal education. Our research has impact. And so without further ado, I'm going to stop sharing my screen and hand over to Aonghus. Aonghus, I'll let you take over the screen.
Okay. Thanks a lot, John. Thanks for the introduction. Well,
as you're taking over, Aonghus, I suppose just to highlight to everyone, please do add your questions into the chat and Q&A section. We'll come to the Q&A at the end of the session. And I can draw upon you to either ask you if you want to turn on your mic and answer the question, or I can throw questions towards Aonghus. We'll try to finish up at 10 to, as I said. So Aonghus, over to you, and thank you very much.
Thanks a lot, John. Okay, so thanks, John, again for the introduction and the opportunity to take part in the series. I think it's a good initiative. So as John mentioned, you can see the title of my talk is about research commercialization for climate action and focus on small hydropower. And so I'm kind of telling a historical journey here about the process of going from an idea to a commercial enterprise, carrying out the idea in practice, and also then a little bit about the actual use of small hydropower in existing water infrastructure systems is the focus of the work. So in things like built water infrastructure like drinking water or irrigation or process industry that uses a lot of water like mining and so on. So you'll see that as we go through. So I'm sort of taking you on the journey, and it's a long journey. Nonetheless, John pointed out, and lots of things have to go right for the idea to work out to be a successful enterprise. But I'm not going to give away any magic formula, which I don't have one, but nonetheless, the story might be interesting. So the climate, following on to put this into a kind of a context of where it is in the National Climate Action Plan and also the SDGs. I've highlighted a couple of those that from John's slides, the powering renewables one and greening business and enterprise. So the story here that you'll hear is about producing hydropower in existing water infrastructure. That has a role to play in contributing towards producing green electricity, because if you're familiar with large hydropower, of course, there are some environmental impacts associated with large dams, which aren't present here. So this is a quite clean hydropower, but it is small, and so the contribution it would make to 75% reduction in emissions by 2030 could be a small one. It probably has a bigger role to play in greening business and enterprise, because again, this, as I mentioned, this is all process industry or existing water infrastructure, which is owned by and operated by some organization, and that organization consumes energy in the process of using that water. So we're looking here at ways of trying to reduce that energy consumption and the emissions related to that. So very much then in the SDGs, this is about affordable and clean energy is probably the main focus, particularly the affordable part. And as a result of that, well, then that's carrying out climate action that reduces emissions, reducing our reliance on fossil fuels, making communities more sustainable and cities, and looking at the process of supplying water and making that more sustainable. And then, well, I've left the quality education bit going because we're telling people about that, including our own students. Okay, so getting into the story of all this, I've put up here on the right an image of the water energy nexus. So a large focus of my own research is in the water energy food nexus, and the diagram on the right is the water energy nexus, leaves the food part out, but that's quite a well-known concept. But if you're unfamiliar with it, it's about the three competing and interrelated resources which are finite: food, energy, and water, and all require each other for production. So for example, it might be fairly obvious that we need water for production of hydropower, but we also need water for the production of oil and the refining processes for fuels for our vehicles, or for cooling various power plants or mining resources. And we need energy for producing water for drinking, or for irrigation to produce our food, and so on. And where this journey of micro hydropower starts is with a focus on the drinking water system. So the drinking water system in Ireland or in any other country consumes a lot of energy, and so I've given some examples there of its global energy footprint, and you know, where it ranks in the UK as in terms of energy intensity. So if you imagine the water system, there are things in there for energy associated with the treatment of water, but also the distribution of it, pumping around. And those pumps, there are many of them, and they're on all the time, and so they consume a lot of energy. And so, take for example, Irish Water in Ireland would be a big, or probably the biggest electricity customer in Ireland. So the journey starts there to try and make this water energy nexus more sustainable. And there are lots of ways you could try to make the water energy nexus more sustainable, like for example, using less water or leaking less water. So if you do that, probably be one of the most effective ways. We wouldn't have to treat that volume of water or pump it around and so on. But here specifically, we're looking at to try and take the idea of small hydropower and incorporate it within the existing pipe networks and channel networks that we have in drinking water systems. And then from there, the idea expanded out into other water sectors. So we'll see as I go through the slides that also included irrigation in Southern Europe, and then industries that use a lot of water, like mining or brewing or power production. So that's the context. So the slides are, yeah, sorry, momentarily not working, but focusing on the idea of drinking water for a moment, and how hydropower can work in there. So if you imagine we can place a hydropower turbine into a water pipeline, and that would produce electricity, but we cannot just do that anywhere. It has to be a place where we have an excess energy, or there's energy that we want to get out of the system. And in water systems, that's at points where we have too much pressure. So in water system, we often want to balance the pressure, not to be too low to have an unsatisfactory service, or too high, which causes maybe bursts or too much leakage. And so in the diagram here on screen, you can see that we're dividing the water network into the transmission side, where we have large pipelines taking large volumes of water from the source to treatment, and to maybe where we might store it centrally. And then on the other side, we've got the distribution network. And in there, we have much smaller pipes distributed throughout cities and habitations. And at various places within those, we will have points where there is too much pressure. And we have existing infrastructure that takes that pressure out, like pressure reducing valves or brake pressure tanks and various things like that. And the idea here in the beginning was to try and replace those with hydropower turbines. And the idea behind those turbines is that they would also reduce the pressure of the network, but as a byproduct produce electricity. So they would perform the same function as the feature of the network that they replace, but also produce energy at the same time. So that energy that's in there in the form of a pressure isn't wasted. So if we have a pressure reducing valve now, that wastes the energy we put into the network to begin with. So we were trying to avoid all that. So that being the concept, going back to this journey kind of starts in around 2010 or 11, so more than 10 years ago at this point. The idea of hydropower in drinking water networks is not a new one. In 2010, it wasn't a new idea. That has existed for a long time. In transmission water networks, where the pipes are large and the flow rate's relatively constant. So you can see a picture there on the right of myself, amazed at this turbine this is one from the Dublin mountains, which produced a small amount of power for a treatment works there. So that's from around the 1970s, and there are older examples of that. But the challenge is that most of the available power in drinking water networks is in the distribution side, where the amounts of power are much smaller, and the number of opportunities are large and spread over a large area. And the challenge is also that the existing technology, so existing conventional hydropower, is too costly for that setting. So when we miniaturize large hydropower devices, which are originally designed to produce megawatts down to the kilowatt scale, which is what we're talking about here, then the cost per kilowatt is just too large. The payback periods are not viable. So there's in 2010 or so, there was a kind of a gap in the market, if you like, where existing technology couldn't be made to work in this setting. So below 20 to 50 kilowatts, conventional hydropower is too costly, also too large, taking up a lot of physical space, and not necessarily capable of dealing with large variations of flow. So the flow chart there is taken from a control valve in Dublin, and that difference in the average flow is more than 50%, and conventional turbines couldn't be able to deal with that. So there were a number of problems that we had to try and overcome. And so the sort of general areas of the research questions that we were trying to address were, first of all, if we take it that hydropower has existed in drinking water networks for a long time, well, if we take all the places where it's possible to do this, leaving the technical challenges aside from it, how much energy would that be? Sort of standing back from a kind of policy perspective, if we were to try and incentivize this, well, what would it be worth doing? That answer was kind of unknown. So we went about to try and develop a sort of a resource map. How much hydropower was there in existing water networks? Then once that was identified, or a little bit in parallel really, we tried to work out, well, we need some kind of an alternative hydropower solution here that puts a lot of emphasis on a lower cost than the existing systems. And if we could solve that, which we did, see, well, how well will that work in practice? You come up with a new technology, you want to prove that it works. So we went into a lot of work on demonstration in a variety of settings, and I'll show some examples of that. And the last bullet point, also we did a lot of work on what were the non-technical challenges to the implementation of this technology. Now, in my presentation, I'm not really going into that very much because the number of non-technical challenges are large, and actually it's quite a bit outside of my own expertise. But one of the things I'd emphasize in the journey of commercialization of some kind of a research device that you might be coming up with, the solution to the challenge is one thing, but that's if you come up with a device, the reason is why it might be used or might not be used has a lot to do with engagement with users of the technology and with sort of stakeholders that are in this policy space and so on. So we did quite an extensive amount of that engagement with stakeholders with the help of experts in that area, particularly in the Trinity Business School, who I'll mention later on. So the journey then, sort of, if you're familiar with on the right here, the technology readiness levels that the EU loves and come from the US, but the technology readiness levels, we started out with an idea back in 2011 to try and put hydropower into water networks. I had worked in the water sector myself in Ireland before I went back to university, and remember working on a job in Sligo where there was a great pressure tank, and I thought to myself, when I was here in Trinity, wouldn't it be a great idea to put a turbine into that? And from that idea, we went to myself and a colleague in the School of Business, Paul Coughlin, who I've been working with on this area since then, more or less, tried to get a small amount of funding to look into the basic technology research idea for this using the Trinity College Innovation Bursary, but we were rejected from that fund. It was a very small fund, and actually we're one of the key parts of the innovation bursary that Trinity was running at the time was it enforced you to collaborate with someone outside of your own discipline. So I had to search around to find somebody who would be willing to work with me on this idea, but would bring a different perspective. And so I managed to find Paul Coughlin in the business school, who was interested in product development and green process innovation as a process, the management of that. And so that really was quite a key step in being able to take something, a technology which I know a lot about, and actually develop it into a commercial product at the end. So we managed then, not getting that funding was probably the best thing that happened to us, and the innovation bursary was quite a success in that it made us go after bigger pots of money. And the first project we worked on was Hydro BPT, which was a kind of a desk study to try and prove the concept, more or less. From there, we expanded into the Durishka project, which was ending later this year, which went into the lab to try and make some of the technology that I spoke about, the low cost technology, and also demonstrate it in the drinking water sector. Third then, or fourth in the list, is the REDAWN project. And REDAWN project was again a sort of a wider scope for this idea of using hydropower in existing water networks beyond just drinking water. So, it turns out that drinking water consumes maybe about 15% of the water resources in Europe, where the other 85 is divided among industry and irrigation. And so we looked into how could we use this technology in irrigation in the southern part of Europe, where a significant amount of the water resources are used there, and also then in water intensive industries. Those two projects, Durishka and REDAWN, involved a lot of demonstration work, taking the technology and running it for at least a year and proving that it worked. And at that point, we were in quite a good position in that we had come up with an idea, proven that it worked, and we're ready to sort of bring it to the market, which was Easy Hydro was born from that. And I'll say a little bit about that towards the end, which also had a lot of support from EIT Raw Materials, which is another European funding mechanism. So going back to the research questions, the first one was, how much resource is available if we could exploit it all in underground water treatment networks or mining or any other form. So we set about it in Europe, or in parts of Europe, collecting a lot of data to try and quantify how much resource there is. And in the diagram there in the middle is try to illustrate, well, some of the places where that might be. So on the right, for example, would be at the inlet to a water treatment plant where the source is elevated and the excess pressure that creates is not required for the treatment process. Or in the, if I just use my laser pointer here, in this diagram here on the left, it might be somewhere in a city, for example. We provide a certain amount of pressure such that we make sure that we have a satisfactory minimum level everywhere. And inevitably, because of the variation in elevation, the ground goes up and down, and also not illustrated in the diagram, the amount of water we take out goes up and down. All those things affect how much pressure is within the pipelines. We inevitably end up with too much pressure at different points. And in those cases, the practice at the moment would be, or at least at the time, was to use pressure reducing valves or some other mechanism like a brake pressure tank to get rid of that excess pressure, to prevent leakage most of all. So we took those two locations and a whole variety of other places and expanded this idea to try and quantify how much resource there was in drinking water networks, irrigation networks, wastewater, and then various process industries that are water intensive, like mining, paper production, cooling, brewing, pharmaceuticals, and so on. So I'll give a few examples of what that looked like. So this was part of the READ-ON project, which involved 5 countries in the EU. This is there: Ireland, UK, France, Portugal, and Spain. And we went around collecting data on the existing water networks, and you can see in the diagram there from Scotland, this is all of the pressure reducing valves that in the database that was available to us with the thanks to Scottish Water. And you know, you can see sort of the little dots there are colored by the size of the average power available. And of course, the power would vary day to day, but this is sort of the yearly average. Most of it is in the 5 to 10 kilowatt scale. There are a few examples above 50 kilowatts where you could use conventional machines, but for the vast majority, it's much smaller powers distributed right across the sort of urban or the population centers of Scotland. And for that reason, we need a technology that is not the conventional hydropower. Now, not shown here there are lots of other things in Scotland where we could use hydropower: the inlets to water treatment works, the outlets to wastewater treatment works, break pressure tanks, and so on. And all those things were formed into a sort of GIS database, which the outputs of which are published, and I'll give a web link to that later if you're interested. So I've got an example similarly from Wales. We didn't manage, you know, if you're familiar with getting data on water networks, sometimes it's a challenge. We can't say that we got absolutely everything. We've got quite a large data set, and from that we're able to extrapolate across Europe as to what the potential would be. So you can see in Wales we had fewer examples of PRVs there, but still a substantial amount of power. 1,100 kilowatts there estimated. And then I also mentioned we went in to look into the potential in irrigations, which were in Southern Europe. So this, for example, image looking a little bit different to the previous one is from the Seville and Cordoba regions of Andalusia in the south of Spain. So in this region, you know, around 80% of water resources are used in irrigation. So when you're, you know, enjoying your orange juice or you're searching the shelves for tomatoes, which is in the news at the moment, those products use a lot of water in their production, and also they use a lot of energy pumping that water around in pressurized irrigation systems. And for hydropower, it's actually quite an interesting technical challenge, because that water is only consumed according to the irrigation season, which is very intensive in July and August, and at this time of year probably is no flow whatsoever. And the water infrastructure is also very, very large in comparison to what we would typically see for drinking water. So we had, you know, have pipes up to diameters of 1.2 meters in diameter. In these networks, the challenge of collecting the data, pressure reducing valves were not so common as they were in drinking water. In this case, we had to model the networks and estimate where the excess pressure is. And so you can see on the map, there's different areas of where the excess pressure is. It was on average 0.16 megawatt hours per hectare. Moving on from that, then, you know, we collected all that data for all of Europe, and you can see that the total amount of it in some of the links I'll share at the end. We went into well, what technology could we use to exploit some of these small scale powers? And we focused on pump-as turbines, and the idea, a pump-as turbine is a commercially available pump which is reversed. So in the picture here, this sort of a green part here is a pump which is just connected in reverse, and rather than being connected over here to a motor, it is connected to a generator. There are some other small changes to the internals of the device, but basically it is a pump operated in reverse. And the idea of using a pump-as turbine was discovered by accident, you know, around 100 years ago. And it produces electricity, but it doesn't do so as efficiently as a conventional turbine, which is designed for that purpose. So there are a number of disadvantages of it. So, you know, up until very recently, it's not a turbine that would have been, you know, a good choice for large hydropower. But for small scale hydropower, it has a very important advantage, is that these are mass manufactured. So conventional hydropower turbines are bespoke, individually produced. So the costs are higher, whereas pumps is the pump industry in comparison to the hydropower industry, there's an order of magnitude between the difference between the two. Pump industry is in the billions of euros per annum. So there are an awful lot of pumps produced. Their cost is between 5 and 15 times less than a conventional hydropower turbine, which makes a huge difference when we're focusing on low cost. The challenge is that when you reverse a turbine, reverse a pump, is so we don't know how it behaves as a turbine. We know that it's possible for it to produce power, but we don't know what its characteristic curves are. So that was a challenge we needed to get over. Also, there was a perceived risk to the investment, because of that being an unknown. The designers of hydropower plants wouldn't really recommend it. So this is an image from that I'll feature again later on, but one of the easy hydro plants in Ireland. So what we were trying to do was to come up with, well, what are the characteristic curves of hydropower turbines? This is sort of the engineering behind it. When we get a number of pumps, they come with a series of characteristic curves, like are shown on the left down here, for example, the head flow curve or the efficiency curve. And in reverse, we don't know what those are. And a pump is substantially different in pump mode than it is in turbine mode generally. So a 1 kilowatt pump could be a 4 kilowatt turbine, for example. And so there are a number of ways of finding that out. One would be to experimentally measure it in reverse, or to use CFD analysis, or to use some one-dimensional conversion equations, of which there are a few around. The problem is that the ones that existed were very inaccurate. They're plus or minus 30%, which is not an acceptable level of accuracy for what we need. And then the other two, CFD and experiments, they're just not practical for regular, projects. That those kind of specialist software or experimental facilities aren't around. Some of the previous conversion equations are shown there, but for example, this, if I take the first one, this is Stepanov method. It gives me the head in turbine mode divided by the head in pump mode was equal to 1 over the efficiency, for example, and that we could use that ratio to try and make the conversion between the two. The weakness of these is that they are all based on a very small number of pumps, and there are many thousands of them. And so as a result of that, the accuracy is very low. So we tried to get around that by just doing more testing. So we built a custom rig pump as turbine testing unit, and built up a system to try and make that prediction on the basis of a lot of pumps and generators and experimentally developed pump as turbine curves. And from that, then we built up a software which allowed us to follow the steps in the blocks underneath, which was to determine the best efficiency point. So this is the optimum operation for my pump as turbine, work out how much it was going to cost and payback, then determine on the basis of that the full characteristic curve of the machine, which essentially means how it behaves when the flow rate changes. And out of that, then we would be able to determine the energy payback and the payback time in years. So that software then had a number of components to it. An input required, we would gather data on flow and head at a particular site. That would be put into our database and would produce the performance curves of an ideal PAT for that scenario. And by an ideal PAT, PAT being a pump as turbine, an ideal being a hypothetical one that doesn't necessarily exist in practice. And from that, the software would produce essentially a kind of a contour. We'll see an example in a minute, but a contour like this in this QH space. And everywhere in there would be an ideal path that would produce a certain amount of power. And in this particular scenario, where my red pointer would be the perfect place to produce most energy. But it's not necessarily the case that a pump is available on the market in exactly those coordinates. So we would then try and find the closest available unit from that. And we can run the software for a variety of uses, maximizing the energy or minimizing the payback period and so on. So next, well, I've got a shot there of the custom rig. The process was essentially building and designing this pump test unit. We cannot see quite all of it here, but essentially as a hydraulic circuit, we have a reservoir of water that gets pumped around out of the screen here and through. This is one of the pump as turbines here in dark blue. and we can test, you know, how it behaves in reverse using our software and going through that kind of a process. So the software then was based on the testing, and then we used the software to come up with a relationship between the flow and power and some characteristics of the machine, the specific speed, and you can see that that relationship is a fairly good fit. I mean, some of the weaknesses of our system are that we focus a lot on single stage centrifugal paths, which were initially down here, which cover quite a broad range of flow and head, but we have got less data in the higher specific speed area, but there's less call for that kind of thing. This is a typical output from the software from an Italian water network. You can see that essentially the software produces a QH space. Everywhere in the contours is an ideal pump, a turbine, for example, that will produce a particular payback period or power output, and that is mapped against known available pumps on the market. Right? So there's a particular group here or there that would probably be a good choice for this particular scenario. And so on the basis of that software, then we went about and said, right, we believe our software is going to work, and we're going to try it out in a number of places. And part of our funding was to go and do that. So the first plant we tried was in at the head of a treatment works in Ireland, in Wexford. This is an image of it, the Blackstairs Group Water Scheme. That lowers it's a small, that's the pump as turbine there. It is a small unit, but lowers the power needs for that plant by a quarter. Well, say 25 to 20% of the time, because there are variations in flow coming in and going out. We also did some networks in southern Spain. We did some run-of-river examples in Wales, and also some deep mining in Ireland. I'll show you all of those. Very briefly, I'm going to come out of this and show a quick video of the Blackstairs example, which was taken with a drone. But in Blackstairs, water is taken from the Blackstairs Mountains out of a little stream here into this is the intake, and that has flown for many, many years down the mountain and ends up in a raw water tank where the pressure just spills into the tank. But we don't have that in the video, but you can see the lovely scenery of Wexford here, and in the foreground now is the small treatment works. What happens now is there is a bypass through which the flow goes into this turbine. You can see here before it goes into the raw water treatment works, and that produces a portion of the power required for that plant. So if I go back to where I was, then this is in Andalusia, in Palma del Rio, which is between Seville and Cordoba. If you're familiar with that part of the world, lovely part of the world to be in, although I think it's kind of cold there at the moment. But this is a part of an irrigation farm. These trees here are walnut trees, and we can't really see the detail here, but there is an irrigation network running along each of them. They require a lot of water, particularly in July and August. And that they also have some power demands, which are on this side to do with automatic fertigation and control of the network. Within this house, we have installed a turbine in the replacing the pressure reducing valve. It also was done in connection with some solar panels, which you can see on the roof there, and some batteries, because of the situation here where it's not an all year round production. It's a intensive in the summer and nothing in the winter. And so that was able to replace entirely a diesel generator. So not only makes it entirely self-sufficient, but reduces the air pollution associated with that. In the case of that, we have a 3D tour available on this website here, Redawn, that you can go in and see some of that. And similarly, some of the other ones, there are 3D tours that you can see in more detail if you're interested. Our run-of-river example was done in the UK, in Wales. This place is called Timar Wubernant. It's a 15th century farmhouse owned by the National Trust, and it housed the translation of the Welsh Bible, or the Bible into Welsh. And so it had a power demand required to keep the humidity and temperature in there around a certain value. And we used a stream which flows under this little bridge here to produce an amount of power for that. And more or less, well, from where this picture is taken, kind of behind it, again, another pump as turbine produced in there to again, on the basis of the software to produce that power. And again, all these were successful and are running, in some cases since 2019, 2020, without major challenges. So getting then towards on the basis of all those pilot plants, I guess there were probably about 5 of them at that point. I did show them some in Portugal as well. One of the PhD students that had been doing some of this lab testing work was Daniele Novara. And when Daniele started in Trinity, he was more interested in innovation and entrepreneurship than he was in getting a PhD. I remember him saying as such during his interview. And he engaged a lot in the Innovation Academy, actually, in Trinity, and was really interested in then taking his research and making a go of it. And so in 2019, we formed a company to try and commercialize this idea. He was also joined by Miguel Crespo, who had worked on the irrigation side of the whole hydropower setting. And importantly, if you're involved in research commercialization and you're from a university setting, you really need to be involved with people who know something about business. And we were also joined by Mike Pedley, who is our commercial director, but had worked previously as the head of the energy section of Welsh Water for many years. And so he brought great experience from actually being the client for a long time for hydropower producers, and just general industry experience. So that really makes a huge difference to the company. And myself and Paul Coughlin then have roles as directors and more kind of advisory role at this stage. So Easy Hydro's probably big break was getting funding from EIT Raw Materials. And EIT Raw Materials, if you're unfamiliar with that, is a funding mechanism that focuses really on the mining sector, on material science. And we obtained booster funding, which was enough to pay for a pilot plant in Tara Mines, which is the largest zinc mine in Europe. It's located about an hour outside of Dublin. That pilot plant we put in place is the first example in the world of a hydropower in an underground mine. And again, it's the same concept in that the underground mine, if you imagine the difference between the top of the ground level and the bottom of the mine is more than a kilometer. So there are huge head drops and water is required. So again, pressure reducing valves exist. So the flows are smaller, but the heads are much larger. So power is available, and that can reduce the net requirements for energy in mining. And of course, mining is not so sustainable, and Tara Mines are very interested in changing that. So the success of that and the publicity around it helped us to grow. And also, again, another pointer on an important point for commercialization is the company also joined an accelerator program, which has a number of elements to it, but it was really training which Daniele and Mike and Miguel engaged in heavily on starting a spin out and making a success of it. So there are many accelerator programs around, and they are a very important part of getting things off the ground. So the Tara Mines project, just briefly a slide on that, was, as you can notice, in the head available was 220 meters, but the flow is quite small. So in the case of the mine, this is a 3D image. I'll show you the actual photo in a moment. Water drops down the mine at various levels, and we have, in this case, pressure reducing stations rather than pressure reducing valves, because the pressures are so large. In our case, we do the same thing as we had done in other settings in drinking water. We make a bypass. Water flows through our turbine. It reduces the pressure in the same way as the valves did, but also then generates electricity for the mine. 30 kilowatts in this case. And so that's from artist impression to actual unit. The pressure reducing valve station is in the back behind this guy in the middle of the picture, and then here's our turbine on the bottom. This one was a little bit different from what we had done in the past, and that's a multi-stage pump, if you're familiar with pumps, as opposed to a single stage. So you can see there are many impellers in there because of the high head. So, and again, this is another advantage of pumps, this turbine. There are so many units around for all of the combinations of head and flow, and any of them we can, not almost any of them, we can try and make into a turbine. Following on from that, we also did a number of projects in drinking water networks in Ireland, in France, in Spain. some in Italy, and this is an example from Fettard Treatment Works in Ireland. It was very similar to the Blackstairs example I showed. So this has an elevated source, which goes into a raw water treatment tank in the kind of background here. And at this point, it's bypassed, it goes through the turbine, produces 10 kilowatts. This project was an interesting one at the time because when it started, it was just before COVID in the planning stages, but by the time it was switched on was after COVID and after all of the enormous energy inflation we've had. And so what these machines allow the client to do is to spend less energy, well, less money on energy, because they produce some themselves. And so the return on investment here became much better. It was good enough pre-COVID, but now it's multiples of times better because of energy inflation. And then last example is an example in a cooling network of an energy production facility. So we know that energy production requires cooling water, which is often pumped through and then has an excess pressure. And here we're taking some power off that and making the process of energy production on a large scale more sustainable. Again, in this one is in the north of Spain, just produced just before Christmas. So I think in the interest of time, I'm going to wrap up here. This will be more or less my last slide. And I just wanted to mention on my last slide that there is something called the COST Pan-European Hydropower Network, which started in September of last year. And that is a fund which funds networking meetings and collaborations, but also short-term missions where students can come from maybe their home country to another. There happens to be one available at the moment to come to Dublin, which pays for up to 3,000 euros for at least a short visit. And so if anyone is particularly interested in anything I discussed, there's an opportunity to come and work with us for a short while. This is particularly for young researchers. So you can contact me about that directly if you want, or have a look on the website there, penhydropower.eu, to get involved. Okay, so thanks for your attention, and I'll hand back to John.
Thank you very much, Aonghus. And for those of you that might be interested in this, we can share the details when we send out the email following the session as well. So stay tuned for the follow-up. I suppose just to kind of close up and give you all a few minutes before getting back to the grind in a few at 2 p.m. Thanks once again. You can find out about what Aonghus contributes to in terms of programs and research via the links in courses and research in Trinity. And just, I suppose, to highlight that the planned talk that was to occur last week by Professor Sarah McCormick has been rescheduled now to next week. So anyone that was previously registered, that detail has been updated. But for those of you who may not have already registered, it's not too late. Next Wednesday, and details will be shared with those of you who are here today. So thank you very much for joining. Well, as usual, we will share a recording of for registered participants of the session in due course, probably Monday morning as our usual time for release. And please do sign up and share details of these sessions. We have them running right through for the next 2-3 months, and we really enjoy having a broad range of people join us for them. So thank you very much once again, everyone. Have a great day, Aonghus. Thank you very much, and see you next week.